This is part 2 of a full review of functions and their graphs, and we are beginning with transformations of functions. So the functions that we just saw at the end of the last video are basic functions, often called parent functions. Basic transformations can be applied to them by adding or subtracting a number inside or outside of the function, or using negatives to flip or reflect them about certain axes. Let's take a look at the parent function of y equals x squared and apply some transformations to this function. Here we have the parent function, and there's a +2 outside of the function. So that is going to march us up 2 units. Here the +2 is inside the parent function, so that's going to march to the left 2 units. In the green example, there's a negative out front of the parent function. That'll flip across the horizontal. And the last example is an example of many different transformations. From left to right, we have +1. We have a negative out front of the parent function, which is a flip over horizontal. And finally, we have a +3 inside of the function, which is a march to the left. Classifying and combinations of functions. Elementary functions can be divided into 3 categories. Algebraic functions, which are polynomials, radicals, and rational functions. Trigonometric functions, sine, cosine, tangent, cotangent, cosecant, and secant. And exponential and logarithmic functions. Let's talk specifically about polynomial functions right now. Polynomial functions will always be in this type of form, in which you have some coefficient a sub n times x raised to the degree of n, and so on and so forth in descending order, all the way down to the constant term, or a sub 0. So all of the a sub i's are coefficients. A sub n is specifically the leading coefficient, and a sub 0 is the constant term. A poly to the 0th degree would look like this: f of x equals a. This is a constant function. For example, f of x equals 7. To the 1st degree, f of x equals ax plus b. This is a linear function. An example of what this looks like. To the 2nd degree will look something like this: ax squared plus bx plus c. That's a quadratic function. Here's an example of what it could look like. And finally, the last major one we focus on is the 3rd degree. That's going to be a cubic function. It'll be of this form, and I'll provide an example here as well of what that might look like. The leading coefficient test will tell us what the end behavior of our poly will look like. If you have an even degree polynomial, the end behavior will look like either the purple or the blue graph, based on whether your leading coefficient is greater than or less than 0. For odd-degreed polynomials, it'll be the same, the leading coefficient being greater or smaller than 0 decides whether it will look like the green or the pink graph for end behavior. A rational function can be written as the quotient of 2 polynomials. Specifically, p of x and q of x are polynomials, and q of x cannot equal 0 because it is in the denominator. Here's an example of what that could look like: a rational function. If you are not an algebraic function, you are transcendental. For example, trig functions. Functions can be combined, sum, difference, product, or quotient of functions using the following notation. So for example, here I am showing 2 functions being added, those same 2 functions being subtracted, what they look like as a product, and what they look like as a quotient, which would make them, of course, a rational function. Besides the algebra of functions, there is finally composition of functions, functions that input into other functions. It will look like f of g of x, and here's an example. I'm going to give us two functions, and we're going to do f of g and then g of f. For f of g, f is the main function, and the g function goes inside, and we simplify. For g of f, g is the main function, and f goes inside that. Functions are even functions when you input the negative of the input, it outputs to the same original function. And they're odd if when you input the negative of the input, it outputs the exact negative of the function. Here I'm doing two examples, even, odd, or neither. I begin just by putting negative x into the function, and I'm going to simplify each piece. Negative x cubed will always end up coming out negative, and minus a negative will be a plus x. And when I go term by term, I'm going to show you here that negative x cubed is the opposite of x cubed, and positive x is the opposite of negative x, and therefore this is negative of the original function. In other words, the answer to this is an odd function. For the second example, g is 1 plus cos of x. Again, first you just input negative x, and then you simplify it. When I put negative x in, I'm going to come across a rule here. 1 simplifies to 1, but cos of negative x, a property of cosine is that it is even, and so cos of negative x equals cos x. And this is the same as the original function, so this is an even function. I'm going to show you here visually that each of these functions is odd or even. So visually, here's what f of x looks like, and we can verify that it is symmetric about the origin. So here's the graph, and I can take a piece that I'll indicate to you with a highlight, and if you take that piece and you reflect it about the y-axis and then the x-axis, that'll give you the resulting remaining piece that is reflective about the origin. For cosine, when I draw cosine to remind you, I'll use the highlighter to show you that this is even, in other words, symmetric about the y-axis. One piece is perfectly symmetric or can mirror across the y.